Students, here we are with perhaps the easiest set of derivative and integral equations, all because the base e exponential function has something very special about it. Notice if we did our red-green show on this, let's just back up here for a second. Let's just do a quick sketch of what we think the exponential function might look like if we do its derivative. We know it's asymptotic on the left and increasing like that. So let's do the red part of the show. It's increasing the whole time, so that means it's going to be positive. And the green part of the show is that it's concave up the whole time, so it's going to be increasing. We also have an asymptote here, so it's going to approach a slope of 0. And wouldn't you know that if it's base e, you get exactly the same thing. So if y equals e to the x, the derivative equals e to the x. Amazing. Such is the power of e. Now, we're going to see this only works for base e. For other bases, you might get an exponential curve, but it's not going to be the same base anymore. If you start with base e and take its derivative, you get e to the x. And so if you have e to the u, you're going to get e to the u times the derivative of the inner function. You're applying the chain rule there. So taking derivative of an exponential function here, we have the chain rule right away on this one. That is, the derivative will be e to the 2x minus 1. You leave that inner function alone. And now we take the derivative of the inner function there. So we get 2e to the 2x minus 1 for the derivative. That's the chain rule. E to the negative 3x. The derivative will be e to the negative 3x again, and now we have to multiply by the derivative of negative 3x, which is negative 3. So the derivative is negative 3e to the negative 3x. Now, locating relative extrema. We're going to need a few pages for this just to do the derivative. Remember, we want to find out where the derivative is 0 or undefined. And it's not over an interval, so we have to assume it's over all the real numbers, and this will work for all the real numbers. So the derivative is going to involve the product rule. We call the product rule. That is, we're going to leave x alone, take the derivative of the other function. Well, the derivative of e to the x is e to the x. And now we're going to leave e to the x alone, take the derivative of x, which is just 1. So we get e to the x times x plus 1 for our first derivative. When we set this equal to 0, e to the x times x plus 1 equals 0. We get e to the x equals 0, and this has no solutions. But x plus 1 equals 0, we get x equals negative 1. So x equals negative 1 is our only root, critical number. And there are a couple ways of checking this. We can check on either side of negative 1 to see what the first derivative is doing, or we can look at the second derivative. And sure enough, it looks like the derivative changes. So let's check that. What's going on? Here's the function x equals e to the x. Let's find f prime at negative 2. Well, remember f prime of x was e to the x times x plus 1. F prime of negative 2 is going to be e to the negative 2, negative 2 plus 1. That's negative. So sure enough, f is decreasing. And now that's what happens at negative 2. Let's see what's happening here at 0. F prime of 0 is e to the 0 times 0 plus 1. That's 1 times 1. That's 1. That's positive, so therefore f is increasing. So by the first derivative test, we have the derivative changing sign from negative to positive, so the function goes from decreasing to increasing. Therefore, we get a relative min. It ends up being the absolute min of the whole function as well. Now, some of you have studied this in statistics, the standard normal probability density function, and we want to show that this has inflection points at plus or minus 1. Now, it looks like you got a lot of stuff in there, but remember, this 1 over square root of 2 pi, that's just a constant multiplier, so that comes along for the ride. And the derivative of e to the anything is itself, again, e to the negative x squared over 2. We just have to multiply by the derivative of the inner function, which is negative x, because you get negative 2x divided by 2, so you just get negative x. So the first derivative is negative x over the square root of 2 pi times e to the negative x squared over 2. The second derivative gets a little hairier, though. For the second derivative, we're going to have to get into the product rule. Let's leave negative x over the square root of 2 pi alone and multiply by the derivative of this. Well, that's going to be e to the negative x squared over 2. Don't forget the negative x again, the derivative of the inner function. Plus, now I'm going to take the derivative of this whole part. So that's just negative 1 over the square root of 2 pi times e to the negative x squared over 2. So, we see we can take out a negative e to the negative x squared over 2 all over square root of 2 pi. And what does that leave over here? X times negative x is negative x squared plus 1. And we set that equal to 0 to look for our inflection points. None of this can equal 0, because this is a constant, and this e raised to a power that's always going to be positive, and then with a negative sign it'll be negative. So we get negative x squared plus 1 equals 0, or x squared equals 1, or x equals plus or minus 1. That's why you get your inflection points at plus or minus 1 on the standard normal curve. And you can prove it's true in general that if you look at the general normal curve instead of the standard, you can show that the inflection points occur at plus or minus sigma, one standard deviation. Now, integration is just as easy. Don't forget your constant of integration. Isn't that handy? So we take the integral of e to 3x plus 1. We're going to have to let u equal 3x plus 1. So du is just 3 dx. So we see we have to sneak in a 3 here, so that means we're going to have a 1/3 outside. So 1/3 integral of e to the u du. So that's 1/3 e to the u plus a constant integration. So that's 1/3 e to the u, which is 3x plus 1, plus your constant integration. Here's a trickier one, where the inner function is clearly going to be this. So let's let u equal negative x squared, because it's inside the exponential function. So du then becomes negative 2x dx. And see, we don't quite have what we want there. We can take the 5 out, e to the negative x squared, and put the x dx here. But see, we want a negative 2. We want a negative 2 in here to kind of complete things for us. So I had to put a negative 1/2 outside the integral. So now you got negative 5/2 integral of e to the u du. So that's negative 5/2 e to the u plus a constant integration. So negative 5/2 e to the u, which was negative x squared, plus c. Now here's just a few more quick examples of integrating exponential functions where you've got something very strange here. E to the 1 over x all over x squared. Now there is no quotient rule for antiderivatives. You can't just take the antiderivative of each. But you can rewrite 1 over x squared like this and realize that if you pick u to be the inner function 1 over x, then du is negative 1 over x squared dx. And so you can set up this way. And with 1 plus e to the x quantity squared, expand so you can distribute the antiderivative idea across all those additions. Now, finding areas bounded by exponential functions. Let's work on A first. Find the area bounded by, here's our graphs, e to the negative x between 0 and 1. So we want the integral from 0 to 1, e to the negative x dx. So, our inner function, we just need a negative 1 in here. So I'm going to sneak in a negative 1 there, and a negative 1 out here. So we get the opposite, the integral from 0 to 1 of e to the negative x negative 1 dx. So we've got the derivative of our inner function there. So it just becomes the opposite of e to the negative x evaluated from 0 to 1. So we get the opposite of e to the negative 1 minus e to the negative 0. So that makes the opposite of 1 over e minus e to the 0 to 1. So we get 1 minus 1 over e. Let's check that on the calculator. Remember how to check it on the calculator? On the TI-89, integral symbol, e raised to the opposite of x, x going from 0 to 1. Let's see what the calculator says. And the calculator agrees. It says 1 minus e to the negative 1, which matches our answer up there. Check. Let's try b now. Integral from 0 to 1 of e to the x over the square root of 1 plus e to the x. Oh, this is a mess. But maybe if we let u equal this inner function inside the square root, 1 plus e to the x, du becomes, the derivative of 1 is just 0, the derivative of e to the x is e to the x, e to the x dx. So that's great. We've got the integral from 0 to 1. Now careful now. Don't forget, you've got the limits of integration are changing. If x is going from 0 to 1, u, which is 1 plus e to the x, that's 1 plus e to the 0, u is going from 1 plus 1 or 2 to 1 plus e to the 1, which is 1 plus e. So in terms of u is going from 2 to 1 plus e, and e to the x dx is du all over the square root of u. So that's the integral from 2 to 1 plus e of u to the negative a half du. We'll continue this on the next page. So that's u to the 1 half, crank it up power, divide by half, which is the same thing as multiplying by 2. And evaluate that from 2 to 1 plus e. So it becomes 2 times 1 plus e to the 1 half minus 2 times 2 to the 1 half, or 2 times the square root of 1 plus e minus 2 root 2. Let's see if the T89 agrees. And the T89 says 2 times the square root of e plus 1 minus 2 root 2. Check. Checks out with what we had. Now, I've trimmed down the exercise to just focus on what you can expect on the big 7, 8, 9, 10 test. Flying job.